Okay, in this problem we're going to think about hobbits and wizards. So we're going to think of this as a speed dating between hobbits and wizards. So we're going to say you have n hobbits and n wizards. We're going to allow n to be some positive integer such that n is greater than 1, just to make this interesting. Okay. And we're going to say we're at a speed dating event, so we randomly pair these hobbits and wizards. Okay. What does randomly pair necessarily mean? Let's think of a specific example. So let's think of here's the number set. Let's think of a specific example over here where we have n equal 4. So we have 4 hobbits, we have 4 wizards. That means we're going to have 4 total pairs. So I'll draw like 4 pairs we're going to have. When we randomly pair, we take the hobbits and the wizards, we put them all together, and we randomly draw pairs out. So we pick 2 people, they're a pair. We pick another 2 people, they're a pair. Totally random. Everyone has equal, probabilities of being paired with anyone else. A hobbit can be paired with a hobbit. A wizard can be paired with a hobbit, a hobbit can be paired with a hobbit. A wizard can be paired with a hobbit, or a wizard can be paired with a wizard. No constraints on that. So maybe an example here is in the first pair we get a hobbit and a wizard. Maybe in the second pair we get 2 wizards. And maybe 2 hobbits, or maybe let's say wizard hobbit, and then hobbit. Okay, this is just one potential iteration. Thing to think about here is that this satisfies the problem constraint because we have we have n hobbits, right? 1, 2, 3, 4, n equals 4, and we have n wizards, so n equals 4 there. So satisfies the constraint. This is one permutation. This is considered one random pairing. Okay. Now what we want to think about is we want to think about x. X is a random variable, and we define x to be the number of match pairs. Okay, number of match pairs. What is a match? We're going to define a match as a pair that's a hobbit and a wizard, or a wizard and a hobbit. Doesn't really matter the order, just that a wizard and hobbit are together. So a match pair is when we have a hobbit and a wizard together. In this case, x is 2, right? Because we have 2 match pairs. This is a match pair. We have one of each type. This is a match pair. We have one of each type. These are homogeneous. We don't have a mix of types. Okay, so that's a match pair. And the problem is we want to solve is we want to find the expected value of x. Okay, on average, how many match pairs will there be? Okay. So here's where we stop and think. We have the problem set up. We understand what's going on. We stop and think, what tools can we use to actually try and solve this? And generally, there's a couple of hints, right? Like, it's really important to be able to pick up on these hints of what type of problem is this, what tools can we use. And the hints here are that we have kind of this big, complex scenario, right? We've got like n hobbits, n wizards, they're all being paired. There's a lot of different permutations. And we're also looking for an expectation. That's another hint. These hints essentially mean that indicator random variables are going to be very useful. Okay, so indicators are going to be useful. We're going to try to use indicators here. We're going to plug in indicators for x within this expectation. So we have expected value of I1 plus plus I. Okay. What are these i's? What do those mean? Let's define ij as the ij as the indicator that, ij is the indicator that j pair is a match. Indicator that j pair is a match. This notation just means, so I sub j, this notation means I parentheses, the indicator of what happens in the parentheses. Sorry, it's really sloppy, but you sort of see what's going on. So this indicator is the indicator that the first pair is a match, as a hobbit and a wizard. Here, right, I1 would be 1 because the first pair is a match. Then, plus I2, in this case, I2 is 0 because the second pair is not a match, etc., etc., etc. This is a big step, right? Writing x in terms of these indicators, but it makes sense. Think about these indicators as kind of light bulbs that are 0 when there's not a match, and they are 1 when they are a match, and we're just adding up across each of the pairs. Since we're adding up all of the pairs, we should get x. It is equal to x. We're adding up the 1 if a pair is a match. That's fine. Okay. Bilinearity, right? We can, even though By linearity, we can just take the expectation of the sum. So instead of just the expected value of all of them, it's the expected value of I1 plus blah, 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 plus the expected value of IN. Oops, no chalk. Plus the expected value of IN. Okay? And this is okay even though the indicators are dependent, right? Like if I know that everyone matches except for the nth pair, and I didn't observe the nth pair, I know that the nth pair must match because there's one hobbit and one wizard left. Think about that a little more does it make sense? But these are highly dependent indicators, but by linearity, it doesn't matter if random variables are independent. I can still kind of add the expectation out, so that's fine. And now I can simplify this one more step, right? By the symmetry of the problem, like the pairs aren't sort of different at all. The expectation of the first pair being a match is the same as the expectation of the sixth pair being a match, as the nth pair. They all have the same expectation of being a match. It wouldn't make sense if they were different. It's totally symmetrical. So it simplifies to n expected value by 1, because all of these are the same and we have n of them. So that's a simplification. So pretty good for us, right? Like we started with this pretty kind of nasty setup. We broke it down, and now we're just looking for one expectation. And we can even use the fundamental bridge to go from expectation to probability. This is n times the probability that I1 equals 1, aka the probability that the first pair is a match. And this is actually not a terrible probability to find, as we're going to see. Okay, so what's the probability that the first pair is a match? And first, let me copy my n. This is just the sound I'm copying over here. Now we're going to find the probability. Well, we can use naive definition of probability, right? Like, let's think about picking the first person, the first whatever in the pair. Okay, once I pick the first, like let's say here I picked a hobbit. That means for the next person in the pair, I have 2n minus 1 choices, right? Because overall I have n plus n, 2n hobbits and wizards, 2n people total. Once I pick the first person, I take one person out of the population, I have 2n minus 1 choices left for the second person in the population. Okay, so that makes sense. How many people do I have such that this makes a pair? Well, I took a hobbit out of the population, but I still have n wizards, right? So I took a hobbit, I put him in my first slot, that means I have 2n minus 1 total people left, but I still have n wizards left, so I still have n in the numerator. It's the same if I picked a wizard first, right? I pick a wizard first, I have 2n minus 1 people left, I have n hobbits left, because I didn't touch the hobbit, so it's still, in all cases, it's n over 2n minus 1, and that actually becomes our answer. Okay, so takeaways from this problem, sort of try to recognize when we see something as indicators. This would be, I think, way harder if you tried to brute force it or think of like, the probabilities of all the different pairings. It's way easier if you think of X in terms of the indicators, break it down by linearity, symmetry, fundamental bridge, and you find yourself just finding a single probability.